So if we have two pixels which are close to each other, but they have very severe difference in their intensity, then the interactions should be smaller. If they are close and they are similar, then the interactions should be stronger. And I'm considering basically two versions of these methods. The first one is a very simple grid CRF, which looks at only the nearest pixels. So we're looking at the nearest 8 connected neighborhood. So we have 8 neighbors, the one to the top left, left, bottom, and so on. And we're also looking at dense CRF, which basically span a fully connected pairwise field over the whole image. And as for the practical issues, I used two solvers. The first one is popular GraphCut, and this one is used for the grid CRF. And I used a new method of iterative mean field approximations to obtain the result for the dense CRF fusion. Okay, so this is the configuration of the experiment scenario. And as for the data set, I created a data set of realistic forgeries. For this particular experiment, the data set contained 120 realistic forgeries with images from 3 different cameras. Right now, this data set is slightly larger because I extended it over the next month. Right now, the data set contains 220 images. If you'd like to use it, you can obtain a copy from here. The images are full HD size, so 1920 versus 1080. The exact procedure how this was obtained, you can get it in the paper. This data set is pretty challenging, meaning that the forgeries were prepared in modern photo editing software. They represent various forgeries, including copy move attacks, including splicing, including some color changes that are basically not really detectable. If there were objects inserted, there are going to be new shadows, new reflections. These are things which are very difficult to handle in practice. So if you like, you're welcome to take a look at this data set. Okay, and these are the results. I will comment them very briefly. So first of all, individual detectors, they don't perform very well. So maybe let's focus on the S-score first. This is the CFA detector, the black line here. The PRNU detector itself is not also perfect. This is this line in here. So you can see that the performance of individual detectors is far from perfect. When we combine the results with standard naive approaches, we can get to here or to here. So when you look at the top performance, so the top score for different thresholds, you can see that the scores for individual pixel-wise methods are pretty similar because the product fusion is 0.61, the empirical fusion is also 0.61, the disjunction fusion is, so the OR is also around 0.6. So the differences between the individual models are not that big. There are some differences in the shapes of the curves. So you can see that one peaks here, the other one peaks here. Why? You will see this a little bit later. But what is important to note is that when you look at the conditional random field models, they can get actually considerably better results, and you can see this both in this chart and also in the traditional ROC curves, where here you can see the individual models. Here you can see a cluster of naive pixel-wide fusion methods, and here you can see the results of CRF fusion. Now, when you look at different images, so let's assume that you can adjust the threshold for every image on its own, and then we will get something which I call the peak F1 score. So if we compare these scores for different images, this is what you're going to get. This is the result of the simpler CRF model with only small neighborhood interactions, and this is the more complicated CRF with fully connected interactions. So you can see that basically there's very little difference. The histogram is basically a symmetric distribution around 0. So we don't see any quantitatively important differences between these models. When you compare the CRF models with the pixel-wise models, the difference becomes clear. So first of all, most of the points on the scatter plot are in the upper triangle, which shows that practically all of the images were improved. And also the histogram of the distribution scores is highly biased towards positive values, which also shows considerable improvement. When you look at the product fusion and the empirical fusion, so the one learned from the data, again, quantitatively, there's little difference. Most of the scores, they cluster around the diagonal. The histogram is also nearly peaking around 0. So quantitatively speaking, there's little difference. So now, I like to show some of the practical results. So these are some examples of the forgeries. Here you see a tampered image. Here is the tampering map returned by the CFA detector. Here is the tampering map returned by the PRNU detector. And in this row, in the middle, you can see the results of naive fusion. So this is going to be different pixel-wise approaches. And the interesting difference is that the empirical fusion is much more attenuated, and the product fusion is a little bit more noisy. So this is the first observation, and you can also remind yourself that this is exactly what we saw on this chart, because the product fusion, it peaked over here, so for lower thresholds, but the product fusion peaked here for larger thresholds. So this is actually perfectly supported by what we see in here. And actually for visual inspection, this kind of result might be much more intuitive. Now, when it comes to the random field models, I'm going to show the final decisions, because this is what the models actually produce. So you can see that the inserted object here very well matches the actual object in the forgery. And this is what we expect, because we have driven the algorithm with image content. So in this case, you can see that there's an inserted object. It's closely followed. This object was actually removed, so you don't see the content guidance here. So this is another example. You can see again that in this case, the CFA map was completely useless, but the PRNU map was pretty useful. And the fusion results are still more meaningful, because even though the PRNU map did not help us to localize the forgery, it allowed us to eliminate some of the potential false positives in other parts of the image. And again, the CRF models, they can follow the object more precisely. In particular, the dense CRF model, which includes longer interactions between the pixels. Okay, so these are some more examples. You can see that in all of the cases, the shapes are properly followed. This is yet another example. In this case, the CFA detector was much more helpful than the PRNU detector, but in any case, the fused result is much more meaningful to prospective analysts. Okay, so I have a few more examples, but the actual point that I'd like to make is a little different. Okay, in this case, we can see that one forgery was detected by one detector, the other forgery was detected by the other detector. But when we combine them together, we can get both. So this is actually the behavior that we expect from fusion methods. But what I would like to focus on is one thing. One of the reasons why we don't see the differences between many of these models is that we're using metrics which are imperfect, to say at least. Because what everyone is using, we're basically looking at some metrics like accuracy or F1 score, but everything is computed on a per pixel level. Now, why is this a problem? I have two examples here, and I will show you both why these metrics are imperfect, and also I will show how does this method behave in case of object removal. So first, let's look at the fourth column here. Here you can see the result of product fusion for two different forgeries. And the scores that were given by existing methods is, for instance, 0.844 according to the F1 metric, and here we have 0.8 nearly. So now, if we change the fusion method from product fusion and use a conditional random field, we're going to get something like this. In this case, maybe one more remark. The red lines represent the ground truth. The green lines represent the detection result. So one thing to notice is that if we go from the product fusion to the CRF fusion with content-dependent interactions, you can get much better results because you can see that the object is followed very closely. You can also see that here the shape of the boat is also much more precise. However, if you look at the score, in this case, the score improved very, very slightly because we jumped from 0.8 to 0.82. In this case, the score actually deteriorated significantly because we're jumping from 0.84 to 0.66. So here you can see that despite the fact that we have much more meaningful detection, the score actually suggests something completely different. And one of the reasons for this is something that I called collateral damage, which basically means that if I'm inserting some object, typically the brush that I will use to put it will be larger. And as in this case, you can see that even though I inserted just the window, I also modified some pixels around it. And this will result in blending. And if we blend the two images together, then this is typically not going to be detectable by any of the methods. And this is something that we don't really care because in this case, I didn't really intend to change these areas. They represent the same semantic content. So there was a wall here before, and there's the wall here after the forgery. So visibly there are no changes to this content. But nevertheless, this is something that is not taken into account at all into existing evaluation protocols. And when it comes to the second point that I would like to make is what's going to happen if I change the image. So in this case, you can see that I was guiding the fusion process by the inserted window. Now, if I don't guide the process, if I guide the process by the background, so this is basically the case of object removal, you can see that the result is still here. The only difference is that we're not following an object because there's no object to follow, but the result is still meaningful. The fusion is still exactly as we wanted it to be. The difference is that the shape is more coarse. It doesn't follow any semantic content. And now when you compare this to the case of a simpler random field where no content is used at all, then you can see that the results are almost the same. So in case of object removal, this technique will just fall back to a simpler scenario where we cannot guide the process. Okay, so to quickly summarize, because we're running out of time, even though naive fusion can help, disjunction fusion it might be interesting because it allows us to customize post-processing. Product fusion is not an accurate model, but it appears to be working well in practice. There is a scale discrepancy between different detectors, which means that we should look at the image content during fusion. Fusion in localization should not be looked at only from the perspective of the combination rule, but also from the perspective of a larger picture. We can use the CRF model for this problem. It can be easily used with content-dependent interactions, which can exploit the image content. Existing evaluation protocols are not perfect, and this requires future work. So basically, this is the summary of what I've been doing. There are some limitations, but because we don't really have time here, I will maybe skip this part. So thank you for your attention. If you're interested, this is my contact. This is the website. You can go there and download the paper. You can download some supplementary materials. You can download the data sets. Some of the source code is also already available online. So if you want to use it, you're free to do so. Okay, thank you for your attention. And if you have any problems, any questions, I'll be happy to answer.
Yep. So we are a little bit late. So if you have some question, go to the break and ask question to the speaker. Thanks again, the speaker.
So the time of this break, perhaps? So right now we have scheduled the breakfast for this time.
In the paper, no, but it's online.
Have to look
Okay. So the speaker is arriving. Maro. Sorry?
Mic him up. Mic him up.
You are talking?
I'd like to mic him up.
Yeah. The next speaker is Mauro Barney, and it's on adversary aware data-driven detection, a double JPEG compression, how to make counter-forensic harder.
Hello, does it work? Yes, it works.
Okay, thank you.
Okay. So thanks everybody for being here after the break. Thanks for the introduction. So this paper, I mean, the title has already been said. This paper is the result of a joint work between my group, so that is me and my former student Benedetta, and Jipeng Chen, who was a visiting student in my lab 1 year ago. Part of this work has been funded by the Medi4 program that was introduced before. So we are already in that line. So what am I talking about? So the contribution is that I will present some new episodes, some new steps in this tug of war between the forensic analyst and the attacker. That's too strong. Okay. And the attacker. And then I will take two different points of view. From the point of view of the attacker, I will present an improved version of universal attack against double JPEG detection. The reference is here. The old one is here. And then from the point of view of the defender, I will show how we can counter this attack and more in general other attacks by developing an adversary-aware detector, which in this particular case is based on SVM. I will present some results when these two players behave in this way. And then I will draw some conclusion, presenting those that, according, at least to my point of view, should be the next episodes in this tug of war between these two players. So the universal attack, this is the basic idea. So here you have the defender's perspective. The defender has two classes of images, single JPEG and double JPEG, and he wants to draw a region, a classification region between these two. So by relying on some classifier, he's able to distinguish these two classes because these classes are rather well distinguished. Then what does happen to the attacker? The attacker, okay, we assume here that the attacker has a limited knowledge about the defender's classifier. So he only knows the feature space. In this particular case, the feature space is defined as the histogram of block density coefficients of the image, all the frequencies. So all the histograms over all the frequencies. So indeed, the attacker does not anything, only the feature space. So what he can do is that he can create its own examples of the two classes. So he builds a class of single JPEG, double JPEG. They're not the same used by the defender. And then, since he does not know the boundary, because he does not know the boundary used by the defender, he will try to take some single JPEG images and bring them as close as possible to some selected targets in the other class. So ideally, you should be able to bring one of these and bring it exactly on top of one of the others. Because if this is the case, the goal of the defender will be impossible, because if I am able to bring this here, then it's impossible for the defender to distinguish these two images, because in the feature space they are exactly equal. So let me put this at work. So this is the general idea. Given one image that has been compressed twice or more, the attacker has a reference dataset. So this is a data set of images that have been compressed once. So the attacker looks into this data set for one image whose vector of histograms, histogram of all the stick coefficients, is as close as possible to the double JPEG histogram that he wants to counterfeit. And then the attacker computes a transformation map that is able to bring the source histogram of the image under attack exactly, as close as possible to the reference histogram he found in the database, and that belongs to a single JPEG image. Doing so, he must respect distortion constraint. And then the attacker applies this transformation to the image, trying to make the image as visually pleasant as possible, so trying to minimize the perceptual distortion. So this is the general idea. And this idea is not new. We already presented this in that previous paper. Here we are introducing a couple of improvements that turn out to be very effective. They both refer to the retrieval phase when the attacker looks into the data set for the target vector histogram. So first of all, the search. In the old paper, we were using a disjoint search. So the attacker was looking for the target histogram at each frequency separately. This, of course, is good if the database is not very large, because it's not easy to find a vector of histograms that are all equal. But from a security point of view, this is not good, as we will see later on. So we propose here to run a joint search. So we look not only for single histograms, but for the whole vector of histograms to be as close as possible. We also introduce a kind of hybrid approach where the DCT coefficient, the DCT histogram, is searched for independently, and then all the other AC histograms are looked for jointly. Finally, we have another change. We use a different metric. In the old paper, we were using the divergence, Kullback library distance, as a metric. Now we're using the EMD. EMD is the earth mover distance, which is the minimum cost I need to pay to bring one histogram exactly onto another. The difference that the divergence only takes care about frequencies, but there is no metric behind it. While this earth mover distance is better because it also considers the cost of moving one DCT values from one bin to the other. So as an example, this is an example of attacked image. So this is the original, this is double compressed, and this is the remapped. They look very similar. Indeed, they are, this attack is carried out by a maximum distortion equal to 4, and the attack is very good, and the PSNR is 38, but there is some attack. If you look at the zoom version, you see this is the original, and here you see some artifacts that have been introduced as a result of the attack. This attack turns out to be very effective. This attack is universal because we do not exploit the knowledge of the detector, and so we could test it against 3 kinds of classifiers. This is a very well-known classifier in steganography, and this is based on calibration. The second one is based on Benford's law. It basically computes the statistics of first significant digits of the DCT coefficients, and then it builds an SVM classifier on them. The third one is the most general because it considers all vectors of all the histograms of all the DCT coefficients and feed the SVM with all these coefficients. So this is a very general approach that does not discard any information for classification. And the attack is very successful. Okay, this is the experimental setup. So we consider the RISE dataset. You can find it here. We consider 700 images in the dataset. Then we compress them once with these quality factors and twice with these pairs. And then we train the classifier, these 3 classifiers, with these images. Then we consider other 300 images, same stuff here. But then the double JPEG were attacked, as I told you before. And we use a reference dataset made of 2,000 images still taken from RISE dataset. And then you see the attack is very successful because in the first classifier, without attack, the AUC was 93, and with the attack, the AUC with all three detectors, with all the three search methods is 0.4. So basically this is a random guess. The same for the other two detectors. Without attack, the AUC was equal to 1, so perfect classification. But with the attack, the AUC drops to 0.50. So basically this is a random guess. But from now on, I will consider only the third detector because with attacks, this is the one that performs better. But for the others, everything is similar. With regard to quality, the quality is quite good because the mean PSNR is between 30 and 35 across the data set. So now we have a very powerful attack, and what can we do as a defender? Okay, the first answer is obvious. We change the feature space. Here we are considering only first-order statistics in the density domain, so we could do better and pass to something like rich features or something that takes into account second-order statistics. But this is obvious, but what I will propose here is something different, and it is something that strangely has not been done very often in the literature, but it's quite obvious. So why not training the classifier so to be able to recognize also attacked images? Because I can suspect what the attacker does, so I could train my classifier to recognize these images as well. So this is what I'm going to do. So without these attacks, this is the boundary that I had before, but now I can generate some attacked images myself, this red, and ask my classifier to be able to distinguish these also. And so I can come out with a new boundary, which is now much closer to the double JPEG, to the single JPEG region. And so it is able to distinguish between these two classes more closely. This is what we will do. In doing so, we can have two possibilities. So we can build a ternary classifier, which is different than here. In the ternary classifier, I want to distinguish the three classes. Or I can build a two-class classifier where attacked and double JPEG images are treated in the same way. For sake of brevity here, I will report results only regarding to the ternary classifier. But very similar things have been obtained for the two-class classifier as well. So again, the experimental setup is the following now. Still raised data set. I only present results for one quality factor for sake of brevity, again. And here, this is the setup, and now you see the difference. Same data set as before, but now in the training, I also build a set of attacked images by relying on my own data set. And then the same for the test. 300 images, same quality factors, attacked images, and then have the test data. So these are the results. Okay, so consider first the case of maximum distortion equal to 4. Now you see that the detector is able to do a pretty good job. So for the single class, single goes to single, single goes to single, single goes to singles, double is perfect, 100%. And for the attacked images, you see, in the case of this joint search, all paper, nothing works, and the attack fails. The detector is able to distinguish with almost perfect accuracy this. With the partially joint search, again, the attack fails. And even in the joint case where the distortion is a little bit more, still, the detector is able to classify correctly 75% of the attacked images. This is not perfect, but it's not bad for such a strong attack. When we increase the distortion, things go a little bit better for the attacker, but not that much, because still, in the most favorable, in the best case for the attacker, you still have that attacked images can be recognized with a probability of 70%. So this is not exactly what we were expecting. So what? So let me try to understand why this happens, because the attack was thought to be very powerful. So I will take this perspective, the perspective of the security margin. There is a very complicated theory behind these ideas, but I can explain this very, very simply in this case. So, suppose you have H is the histogram of the CT coefficients of image Y at frequency ij. So now I have two images, X and Y. This is the source, this is the target histogram. And then I can introduce this EMD, which is the distortion that the attacker needs to introduce to bring X exactly over Y. In poor words, this is the security margin, the EMD. If the attacker is able to do this, then no way. It's not possible in this feature domain to distinguish these images. So this is what we want to do. And this gives a practical idea of how much distortion I need for a perfect attack. So we computed this quantity for all the images in the test dataset by using the reference database for the target histograms. And this is the histogram of the security margin. Well, this is the maximum distortion you need to introduce across all frequencies. So if you want to be perfect, you need to bring all the histograms over the target, and this is the maximum you need to do over all frequencies. And you see the distribution. The average distortion you need to introduce is 23. And if you want 95% success rate, you need to introduce a distortion which is 50. This is by far too much. The idea is that these images, at least in these data sets, are quite far enough. If I want a perfect attack, that's not easy at all. So I have an idea here of what this means. This is original remapped with d equal to 4, so good. But when I apply 23, you see that the distortion is bad. And I am able to apply this and have a perfect attack only to 50% of the images. So this is not even enough. So this is too much. So the attacker is not easy. Well, there is another small thing before concluding, is that in the previous results, these two data sets were equal. So it was assuming that the defender can train by creating attack the images by using the same reference database used by the attacker. Well, this is not reasonable, so we redid our experiments by using two different data sets here. So the attacker uses a data set, and the defender has a different data set to simulate what the attacker will do. So this is worse for the defender, yet the attack is only a little bit better. If we do everything, you see that the performance of the adversary-aware detector drops a little bit, but not that much. Still, with this distortion, this is d equal to 4, but with d equal to 8 is similar. This distortion is not enough to create a perfect attack. The idea is that the security margin, the distance between the two classes, is too much to have a perfect attack. Now, let me conclude. Is this the end of the tug of war? No, it's not at all. So first of all, we have proven that building a successful attack is not as easy as we think. Because usually, in most papers, we do not consider the possibility that the defender train his classifier so to react to attacks. Then, the next step. From the attacker point of view, the lesson that we learned is that if we stick to a mean square error distortion, no way. Because this is more or less the best we can do without knowing the details of the detector. But our impression, my feeling, is that the model is not good. We should not rely on mean square error distortion. It's possible that we can create other attacks like geometric distortion, Wiener filtering, whatever, many things that can introduce a larger distortion but with less perceptual degradation. So perception is very important here, as it was in the old days of watermarking. From the point of view of the defender, the idea is that we should, for sure, pass to higher order statistics, because if I have more rich features, then everything will go better, for sure. And for sure, to exploit the idea of the adversary wear detector as a way to prevent possible attacks, because this seems to be very powerful idea. Okay, that's all. I don't know if there's time for questions. I didn't take the time, so.
Okay. So we have time for just one small question. And if you do not have, I have a question. So my question is about the defender. Your approach seems to put the border of the class very close to your object, to your sample. What about overfitting if you want to be a defender with another database? I mean, if
No, I understand the question. Yes,
okay.
I understand. So the idea is that, okay, in the picture I put this very close on purpose.
Yeah.
Because the idea is that we want to train the classifier with the most powerful attack. Of course, we do not have the most powerful attack. There is no such an attack in general. But the idea is that if you can train against something which is very, very close, then all the rest should be out. This, in a way, resembles a one-class classifier, in a sense. But, of course, we know that the problem with one-class classifiers is exactly overfitting. Then you have another database, and then you have other points in the other class that go away. This is a trade-off that is unavoidable. And the hope, but we are still running experiments for that, is that going to a richer feature space, there is enough room to make these classes separate enough. In this space here, with first order statistics, we already know that this is not possible.
Okay, thank you. So next speaker is not there, so we're gonna replace next talk with a talk of name of Shidir Sharma. No? Oh, sorry, Subramanian Venkata. Yeah. And the talk will be about anti-forensic technique for median filtering using L1, L2 TV model.
Good afternoon, everyone. I am Subramaniam, and I am from IIIT Delhi, India. So I will be presenting this paper titled Anti-Forensic Median Filtering using L1 minus L2 TV model. Okay, so here is the outline of the presentation. I will briefly introduce and then move on to the challenges, and then to the problem and algorithm, and then finally go on to results and conclusions. So median filtering has gained a lot of attention in this forensics community, both from the forensics aspect as well as counter-forensics aspects, and then anti-counter-forensics aspects as well. So there have been a lot of works in this domain, and so this paper is about the anti-forensics one, and one of the major works is done by WIFS as well in this domain. So we'll be focusing on the anti-forensics aspect using a optimization formulation using an isotropic and anisotropic TV model. Okay, so coming on to the challenges. So there are several popular detectors for this, and what they catch hold of the median filtering aspects is that is about the stringing artifacts. Oh, sorry. Okay. I'm not sure it's not pointing out. Okay, I'll just show this thing. So in this thing, we see that this is an original image with a patch emphasized, and if you perform the median filtering, then we see this sort of string artifact. So it's basically median filtering is performing a sort of blurring artifact as well. So these detectors catch hold of this blurring aspects and then say whether it is median filtered or it's not median filtered. So if you just take a look at one of the popular detectors, which is second order local ternary pattern features, second order LTP features. So what it does is it's basically taking the patch. Let's say here we take a 5x5 patch, and what it does is it performs a first order derivative on a given pixel. And once it gets this derivative, then it goes on to encode it into 3 different values, -1, 0, 1. And how does it do is basically just taking the product of these derivative values. So if they are different, it encodes with a value of 0, 1. But if one of the values is 0, it encodes with a value of -1. So it takes derivative in 4 different directions: 0, 45, 90, and 135 degrees. Now, okay, let's take a look at the original and the median filtered image. So we have a patch size of 5x5, which is emphasized over here. And if we take the second order LTP features in the 4 different directions, again 0, 45, 90, and 135, we see that for the original one, we see all the 3 values, -1, 0, 1. But for the median filtered, you would see that there is a strong pattern of -1, -1, -1. There are no such deviations from -1. Most likely it's that the blurring that has been occurred because of the median filtering, the derivative has gone to 0. And once it is 0, it's being encoded as -1. So this can clearly demarcate the median filtered and the original image, which is being captured by second order LTP. So the challenge would be to overcome this so that we can preserve the natural image statistics so that it eludes the detection by the median filtering detectors. Okay, so the problem that we are targeting is basically an anti-forensic median filtering operation which can elude detection. So we hypothesize that the adversary has both the unfiltered image and he can perform the median filtering. So he can use all this information, and we create the objective function based on this hypothesis. So moving on to the algorithm part. So we have 2 parts of the algorithm. One which will take care of the visual similarity of the counter-forensic image, and other which will take care of the natural statistics of the image of this counter-forensic image. So coming on to the first term, which takes care of the visual similarity between, so the visual similarity is between the output image as well as the input image, and the output image as well as the median filtered image. So we can use any good distance metric. We are using a squared L2 norm for this purpose. So here is what it is. So we have on the top, we have the first term, which is the distance between the output image as well as the input image. The second one, the output image, y, and the median filtered image, m is any function. Here in this case, it's a median filter function. And x is the input image. So we are taking the distance between the output as well as the input, output as well as the median filtered function. So this is about the visual similarity. Then the next one is about preserving the natural image statistics. So we can use, again, there have been different norms like L1 and other norms as well. So we boil down to this L1 minus L2 total variation model. Okay, so here is the full formulation. So we have the top 2 terms as the visual similarity metrics between the output and the input, output and the median filtered image. And then finally we have this term, which is basically taking care of the isotropic and anisotropic TV model, the difference between the 2. So we have the entire formulation which takes care of the similarity as well as the image characteristics. Okay, so we boil down to this L1 minus L2. There have been several other penalties also, we can include them, but we boil down to this primarily because it has been shown by Tao and An that this can be expressed as a difference of convex components, and once it could be done in that fashion, it becomes sort of continuous function, and in Lipschitz continuous function, and the convergence is guaranteed. So we can have a good optimization solver for this one. Okay, so that's our complete formulation, f of y, where y is the output image that we are seeking for. So we have two terms. The first two terms for the similarity, and the other one for preserving the characteristics of the image. We can express this as a difference of convex functions using tau and Ann's proposal, and once we can do that, we have good solvers like split Bregman solver proposed by Goldstein and Hosham. So we can have this solver, and it basically converges. Convergence is guaranteed. Okay, so I'm not going into the details of this. These are available in the paper. Okay. So for the performance evaluation, we take up 3 different features: global probability features, median filtering forensic features, and second order LTP features. They're all pretty powerful and have shown very good performance for this one. And for the training and testing purpose, we use a CSVM and learn the parameters using 5-fold cross validation. Okay, so this is the data set. We use the BOS-based data set and 512 cross 512 images, all 8-bit grayscale images. So here is the original image. So in the original image, these edges are pretty clear, like the roof edges, the windows, they are pretty clear, and this board is also very, very clear. And this is a median filtered image. If you see the roof, the windows, and this, the visual clarity is lost. The edges have been blurred, and if you see the windows are sort of, the segmentation is lost. It's all merged. So that is what the median filter is doing, and here is the output of the proposed algo. So if you see this, the edges are pretty sharp, not pretty sharp, but it's still sharp as compared to the median filter. And the windows, that demarcation was completely lost, but it is preserved in this. And the visual clarity of this one is also preserved as compared to the median filtered image. So I'll show a side-by-side comparison of this with the original, median, and the proposed output. So here is what it is. For the original, if you see again, so we have those edges clear. In the median filtered, they have been blurred, and in the proposed one, they have been preserved to some extent. So it's not completely blurred, neither it's as sharp as the original image. So we have both the function of the median filter as well as the original image as well. Okay. So if you compare the difference between where is the difference occurring because of the proposed algorithm against the median filter. So here is what. So we have the original image and the proposed algorithm's output. So if you see the difference is primarily occurring at the position where there are sharp intensity changes, basically where there are edges, basically working with the gradient. So the smooth parts are sort of left out, and the differences are panelized. The differences are maximum at the edges. So we see this difference mostly at these positions, which are pretty sharp, where there are pretty sharp changes. Okay, so let's analyze this detector once again. What this detector did was figure out the first order derivative and encode it. So we have the original and the median filter. The median filter, again, we see the pattern is pretty similar in terms of the output value of the detector is basically -1, -1. But for the original image, it's all over, like all the 3 values are there for all the 4 directions. But if we compare against the output of the proposed algo, for the same patch, what we see is now the second order LTP is saying that the values are again coming from all the 3 values, -1, 0, and 1. It's not that, unlike the median filter, the values are not the same. They are not only -1s. So they are all the 3 values for 0 degree, 45 degree, and 135. For 90, somehow it still says purely -1. But there is a clear difference now as compared to the median filter, which would otherwise say only -1s. So we see that the visual similarity is taken care of. We see that the detector's performance would be suppressed because now the output is not going to be only -1s, just like the median filtered ones. Okay, so those were the 2 parameters on which we formulated the objective function. And let's see some experimental results, quantitative ones. So we plot the ROCs, the true positives and the false positives here for all the 3 detectors. So if you see for the low false positives, let's say close to 0.05. The true positives are roughly between 0.65 and around 0.8 for a 3x3 median filter. If you increase this, the kernel size of the median filter, it's like 5x5 or 7x7. The true positives would slightly go up. Obviously, more artifacts are left behind because of the increase in the size. So we see that slight increase in the true positives for 5x5. And so we did for 7x7. Results are almost on the similar lines. And we did for all the composite ones, that is include all 3, 5, and 7x7 size kernels. Again, the results are not very different. They are pretty much on the similar lines of the previous ones. So we see that for a low false positive, the true positives have been quite degraded for these detectors. So we see a comparison against what happens when we haven't performed the counter-forensic operation. So here is the table showing the results when the counter-forensic operation is not done. That is the original versus MF3, median filter for 3x3 kernel, and original versus AMF3, that is the anti-forensic median filter 3x3. So when there is no counter-forensic operation, if we look at the detectors, all the 3, they show a very good performance for both TPR and TNR. Both are pretty close to 100 mark. But once this this counter-forensic has been performed, we see that that sort of true positive and true negative, they show a decreasing trend. It's like gone down to 86% decrease of say around 10 to 15%. So that's again because the statistics has been taken care of. Okay, so finally coming on to the conclusions and future work. So this work was basically about the anti-forensic of median filter, taking care of the image statistics. And the results are quite promising in the sense that the detector's performance has been degraded. It's a generic formulation. We can replace this, the median filtering operation by any other operation, let's say another linear filter, or basically you can take a contrast enhancement operation or any other operation, because the whole thing is that some of these operators, they work on pixel by pixel formulation. If we take care of the neighborhoods, this pixel by pixel formulation is gone, and the detectors would not be able to look for the artifacts which are otherwise created because of this pixel by pixel operation. So in that sense, it's a generic one, and one can extend it to the other forensic operations as well. Okay, so yeah. So that is it, and thank you.
Thank you. I have 2 questions. One is that did you ever try to compare your method with other similar work? I remember it published in Information Hiding. Where the authors formulated the anti-forensic of median filtering as a deconvolution problem.
Oh, okay. The
Okay.
WIFS
You have
problem,
compare. You know that?
WIFS problem, right?
Yeah.
Yeah.
You have ever tried to compare the performance?
So not yet. So there are 2 things again. One, that WIFS technique is basically saying that median filtering has been performed, and let's go back and remove those artifacts. Yeah. But here we are including both of them, like the unfiltered one and the median filtered one. We are including both of them in our formulation. Mm-hmm. So we don't assume that we don't have the access to the original image. Mm-hmm. Because in WIFS work, it's basically median filtered image, and they are going back and suppressing that. But we can say that adversary can have the unfiltered image as well. So that's why we have both the terms. So that is one reason. But in any case, we are in the process of comparing with that.
The second one is, in your proposed method, you require the original image because you use the L2 total variation. But in practical applications, you don't have the chance to have the original image. Yeah. Often you have the noise images, such as a pepper salt noise image, mm-hmm. and the media filtered image. So in that situation, can your method still work?
Okay. So in that case, so my assumption here is that the adversary is creating this thing, and let's say there is a forensic detector who is going to apply any filtering, any detector, either the median filter detector or any other detector which is looking for the linear artifacts. So that's why we perform the median filter in order to suppress them. So there is where this would work, and it would suppress all those artifacts. And let's say you're going to apply a linear filter detector like the CFA interpolator. It's not going to work in that case. So if you apply it on the median filter one, it will show that there is no such CFA interpolation possibly, saying that it's not an original image. Maybe it's coming from a computer graphics site, which is not good for the adversary. So what the adversary would want to do, it would want to show a CFA spike, but not show a median filtering operation. So in that case, it's going to be useful because it shows a CFA spike, meaning that it's an original image. It won't show a median filter operation, saying that it's not been touched by the median filter. Having said that, we haven't really tried with the images which are like have been operated by the salt and pepper noise or the median filter noise, or the median filtering operation. But maybe we can definitely go back and check this thing. What happens in that case? Yeah.
Okay, thanks again.
Yeah. Thank you.
Thank you. So now, speaker will talk about a deep learning approach to image forgery detection. And speaker is Yuan Rao. Yes.
Thank you. Thank you for introduction, and thank you for your kind introduction to my paper. I'm Yuan Yao, and from Sun Yat-sen University, China. And the topic here is a little different from what we have seen in the internet, because we revised our paper, revised title of our paper during the reviewing process. And then our topic is deep learning approaches to detection of splicing and copy move forgeries in images. Sorry. It seems it doesn't work.
If there are other programs, you can open it with other
programs.
Other software.
No. Then how?
Right click on the document.
Is that okay? Okay, thank you. Okay, okay. And I will introduce our work in the following five parts, and because the background of the splicing and copy move detection has been already explained very clear by the previous speakers. So I'm just skip this part. What I want to point out that our research is mainly focused on classifying these two types of the temporary copy move and splicing from the authentic images, and that is a classification problem. And some previous methods are listed here, and we can see that you can use moment features or markup features in spatial or DCT domain to handle this problem, or also add some features in DWT domain, or use or apply a steerable pyramid transformation with local binary pattern, and which will result in a very good detection performance, and also the 2D non-causal Markov model. And almost all of these existing methods are based on the traditional pipeline of feature of machine learning, and which is that is stated. We need to go through some basic steps like pre-processing, feature extraction and feature selection, and then classification use some machine learning tools. So we begin to think that how can we improve this highlight by some efficient feature learning technique, because the handcrafting feature represent the process of handcrafting feature representation is always time-consuming and very complex. Then we naturally think of some very hot technology nowadays, and that is deep learning. And the deep neural networks can extract complex statistic dependencies from the input, and then automatically learn their hierarchical representations. And this figure is a typical block diagram of the convolutional network, which is short for CNN. Then multiple there is multiple learnable filters in the convolutional layer that can be used to convolve with the input feature map, and then activate by some nonlinear function, and then subsampling by the pooling layer. And this convolutional neural network has been successfully applied in many areas in computer vision tasks. Then in the last 2 years, there seems a new trend in the image forensics that has already some works apply the deep learning technology in the traditional image forensics, such as media filtering detection, or splicing localization, or the image manipulation detection. And however, this research has found that the traditional architecture of deep learning of neural network may not be suitable for the image forensic. So they need to add some pre-processing layer, or convert the input feature to another feature, for example, wavelength feature. And then our work, the improvement of our work is that we automate the image processing, process, and then we propose a CNN that can automatically learn feature representations by the proposed network initialization strategy, and then also improve the final detection performance. Okay, here is the framework of our proposed method. The proposed detection scheme consists of two major steps. One is feature learning, and the other is feature extraction. In feature one, in step one, we first sample some patches, and then we fed them into the CNN, and then train the CNN. And in step two, we extract the features from the whole images based on the pre-trained CNN, and then we fuse the features to obtain the final discriminative feature for SVN classification. The patch sampling is very necessary because our image in the data set is of different sizes. So we need to sample a small size patch